Check, check. Check, check, check. I hear myself. All right. Oh, this is on. Slide forward, slide back. All right.
All right. So what I'm going to do is I'm going to introduce you, and you're going to start. Okay. So we are getting over to our next session. Today we have with us Mr. Brandon Ward, and he is going to. Oh, yes, we got some claps. That's what I'm talking about. Let's give it up. We've been drinking the Balls Guarana, I see. You got a lot of energy. Mr. Ward is a cybersecurity engineer with Raytheon Codex, specializing in reverse engineering, vulnerability research, hard target emulation, and advanced program analysis. For the past 7 years, Mr. Ward has served as chief engineer of Codex's cyber vulnerability assessment programs, applying the tools and techniques of the offensive cyber expert to the securing critical systems. Mr. Ward also serves as the site lead of Codex Tampa, St. Petersburg office, and has served as a principal investigator of several DARPA cyber efforts. And with that being said, without further ado, Mr. Ward.
Thanks, everybody. Mic check. Everybody hear me? Hear me in the back? Excellent. All right. Welcome to this talk. Thank you guys all so much for showing up. I know there's a lot of things you could have done today. Besides this, go watch baseball, which I'm going to do in a little bit. But, you know, they thanked me for being a speaker when I got here, but I want to thank all you guys, you know, basically thank all the people who contribute to sort of the Tampa InfoSec community. You know, I think it's growing and it gets better every year. And so that's all for you guys. Thanks. Let's get started here. I'm going to talk real briefly about where I come from. There's a company called Raytheon Codex. We're like a business group within the large thing that is Raytheon. We used to be a company called SI Govs. We used to be called CSI, and now we're called Codex. The big office is over in Melbourne, Florida. There's 300 engineers over there. We've got a small site here in Tampa, St. Pete. You know, we do a lot of this work, you know, a lot of vulnerability research, reverse engineering, a lot of emulation work. You know, a lot of this really just grew over the tech base that we've built over the past 15 years, supporting the VR task, right? Finding bugs, the tools you need to automatically find them, to help VR engineers do the job faster, program analysis, how to expand to ever stranger target sets to figure out how to do the work. Who am I? Will just told you, we don't need to go over that. So cyber vulnerability assessment is probably the most unfortunately named thing. I don't know why we came up with this, because I think the DoD has like the same name for something that they do, and like there's 4 other people that do the same thing. And it's basically to try and do the same job, right? Which is secure, what we call Blue Force systems, secure, U.S. technology, weapon systems, supporting technology, in one way or another. And the way that we do this is we take the existing tech base, existing knowledge base that we have, that we spend a lot of time and years pointing at targets to find bugs, and we point those things at our customer sets, their targets, to basically emulate the same thing. Find bugs, help them patch it, secure the systems. What else? The big thing here is the cooperative piece of this. If someone comes and there's a piece of equipment that falls off the back of the truck, and you ask me to spend X amount of time analyzing it, finding bugs in it, there's this massive upfront reverse engineering effort. You throw like a series of binaries at me and give me, tell me to look at them, you're going to spend the majority of your effort for the first X amount of months trying to figure out, what is this thing? What target is it? What architecture is it? What does it do? And the real thought is we shouldn't have to do that with our own systems, right? Bring in the system stakeholders, bring in the development teams that are doing that work, have them work sort of hand in hand with us to do that rapid information dump to say, okay, this is what the system does. Here's what the major components are. This is how they talk to each other. These are where the important processes live. Here's the artifacts that they consume. And even further, like, here's the test sets that we use to test the system now. Here's all the test data we use, from functional tests through unit tests, et cetera. You guys should adapt this to do cyber testing, analyze the system, really rapidly, find vulnerabilities and enable the customers to fix them. And the other big thing about this is we talk about actionable vulnerability reports. We only really report out things that we've proven. If I have a fuzzer that has a crash, that's something that'll turn into a report for someone to fix. But if let's say that like you have some sort of, you run some static analysis tool that says, oh, there's a potential vulnerability at this line of code, whatever. We'll go look at that, run that code, exercise that code to see if it's real. So really taking that sort of false positive level that you get from a lot of sort of tooling and just take it all the way to the ground. If I pass over some vulnerability report to one of our customers, that's a thing that we have done on the system, on the code. And what we want to do ideally is be able to pass that information, actionably into the software development chain so that they can fix things, they can write sort of tickets. I always say I do not want to be like sort of like goober consultant, right, who comes back like 3 years later to tell you the same problems that I found like last time I was here. I want you to be able to fix this stuff, and the next time I come over, we can look at some new target set. All right, bad news up front. I swear I have done this, and I have looked at many systems and found many bugs. Me and my team, we are not going to talk about any specific targets, any specific findings. There are pretty obvious reasons for this. Even outside of this space, people are super leery about, even if they found stuff, right? They don't want you assessors to be sharing that. What kinds of bugs are we finding? We're going to talk a little bit about the end, sort of high level, what kinds of things we see. But if you want me to say, oh, in system X we found this vulnerability, that's not going to happen. What else? Okay, so I just want to take a quick survey here just to kind of gauge the room. How many people here are like software developers? Okay, pretty decent amount. How many people here have put their hands on like Ghidra or something like that at some point in life? Okay, good amount. Okay, who here knows what like a fuzzer is? All right, cool. I think we're going to be in good shape. We won't have to sort of walk through a lot of that stuff. All right, so this is our sort of OV1 view of this. There's two major steps to this process, right? When we engage with new customers, we sort of say, okay, what we're going to do initially is this sort of software architecture security assessment. This is pretty similar to kind of lots of other sort of secure systems engineering exercises you're going to see as far as identifying where data comes into the system, understanding how data is passed within a system, how data is trusted within a system, what are the sort of impacts I could have, if I could gain access to a system and do effects, everything from, DOSing a system to full code execution, what kind of, ability do I have to, elevate privileges, pivot through the system, steal data, et cetera. Really to end up with this sort of prioritized list of like, here's where we want to look at this system. And I just give it sort of like for some scale here, right? Let's say you came to me and you said, hey, I want you to look at like a submarine. I would say, that's like way too big. Like there's 400 computers in that thing. Let's spend some time thinking about initially what we want to look at for this engagement, and that for that like subsystem, then we can sort of apply this process and say, what does this thing do? Where are the critical components? What are the ways that attacker can touch this thing? And sort of end up with this sort of prioritized list here. There's one thing that makes this sort of SASA process different, which is the whole time we're doing this, I'm really trying to drill down with the customer to find out where the binaries are, what they're running on, how they're compiled, how they talk to each other, what libraries they link to, what kind of OS protections, config files, data formats. What the ideal here is like at the end of this SASA process, I have like a package that I can hand over to like a VR engineer and they can like go, open this up. I see where the binaries are. I see where all the linked libraries. I could run this thing in emulation today if I wanted to. I can open these things up in Ghidra, start looking, at the code. Although, to an extent, do we really need to spend a lot of time in Ghidra? Like we have source code most of the time, right? So, we get the benefit of not needing to look at Ghidra's, decompilation necessarily because we have the code. I will tell you that we still use Ghidra like a whole lot because it's like the best way to sort of move around in code and sort of follow connections and understand dependencies and stuff like that. But that's a part of this sort of cooperative process where we're like, you got super good code auditors. Give us your code. We'll spend time looking at run tools on it, et cetera. And then this second piece here, which is like vulnerability research. And I always the way I describe it, right? Let's talk about the standard vulnerability research job without sort of this cooperative, effect. There's a lot of reverse engineering here, right? And then we sort of enter this process, which is like a dual static analysis and dynamic analysis at the same time. We've got people tearing apart code. We got people running static tools on these things. And then a lot of times we're trying to get things running either on, in containers, in virtualized environments, in emulation, in order to do what? To basically, normally we basically want to like point fuzzers at these things, send them all kinds of crazy data, get crashes, et cetera. I'm going to talk a little bit about fuzzing in a couple slides because I think it's useful to understand sort of the state of play as far as usefulness of actually fuzzing targets. So you do static analysis and dynamic analysis together. The bugs fall out. You file your vulnerability reports. Any questions? I'm gonna try and stop every now and then, like ask questions. I don't want to just be like a data dump. If anybody has a question, just like raise your hand. Oh, so just to hammer home this whole like cooperative nature of this, we really encourage our customers to like, really cooperate with this as much as possible. This is what happens when you don't. I actually got a message yesterday in Signal from one of my engineers, and it says, in other news, a guy at XXX client is stonewalling / slow walking, providing a software for an audit of a dice. So we got one off of eBay and are in the process of dumping firmware. So we're going to get there anyway. So you may as well help us. So I can't talk about specific systems, but we can have like an idea exercise, or we can talk about this sweet baby here, right? Probably the most wicked weapon system you've ever seen. It's a tank and a sub and a helicopter. And you know, believe me when I say, when we talk a little bit about how this thing would be put together, it's pretty similar to how any other sort of large weapon systems put together. There's pretty standard sort of bus usages across a lot of frameworks. There's a lot of standard usage of the same sort of computing components, operating systems, message sets. You know, it's not unusual for me to walk in and say, okay, I got it. You got a heterogeneous environment with like ARM and MIPS, and they're talking across some 1553 bus, and maybe there's some like space wire over here or whatever. You got Ethernet running in here also. Cool. There's sensors. There's a radio. There's crypto. Cool. So how will we sort of walk through this? I'm going to go through this sort of like SASA process quickly. And again, if you guys have any questions, please call out. And really just going to try and drill down to how we would tear this thing apart. Again, this is way bigger than we ever generally look at for an engagement, but I think it's going to be useful. And maybe you guys can all go home and see if you can purchase your own Olympus off the internet later. So, you know, in the end, you're going to have stuff like this, right? This thing's going to have to do built-in test. So there's probably some master computer to try and run all that crap. There's a bunch of comm systems that probably go into this thing. I mean, heck, this guy's going to need to have like acoustic comms probably for when he's underwater. He's going to need to have like SATCOM for when it's flying around. It's going to have like internal comms on the thing. So probably those things are going to come into the system through their various sensors. They're going to get wired into their, you know, their sort of localized message set, you know, handlers, and they're going to parse, you know, they're going to pump all that to something that's like a comms manager, right? And people who need to get that information, that's going to sort of be dispersed across the vehicle. Loader verifier, you know, you're going to see a lot of these, right? There's generally, I don't know, you know, so a lot of times these things have sort of single software load architectures where when this thing sort of boots up, it's going to push all these software loads to a whole bunch of different systems. And then it's going to say, hey, run CRCs or SHAs on these, do crypto verification, make sure that that is the software that we intended to load onto there. Mission computer, this thing's doing a mission. It's going to have a mission computer, which is probably integrating a lot of this stuff into it between the comms. You know, it's got, you know, when this thing is flying, it's going to have, you know, avionics in order to figure out how to move the vehicle along. Does anyone see like what the worst part of this system is? It's that maintenance laptop. You know, you're lucky if there's one, right? You know, often there's like 5. You know, contractor X has a specific part of the system that they work on, and they show up on site, and then they connect and they upload software, and then they walk away, and then somebody goes, "Who was that guy?" Oh, I don't know. He's the guy from Lockheed who uploads software on this thing sometimes. Like, okay, cool. A lot of times in our engagements, we just sort of assume presence on that thing. As far as trust levels and security levels, it's a juicy attack vector. That thing's, not only is it in transit, you know, it is the piece of equipment which is most easy to abuse. It's the easiest thing that someone's going to plug into the internet at some point, and it's going to end up as a foothold for this system. So going forward, what we do here, see we're doing on time. So as we go forward, this is kind of how the system's, you know, perhaps going to look like. It's got some sort of division of duties on these 3 different 1553 buses that it's using to share data. And there's some unfortunate things that you're going to see in all these things, right? Just some of the worst like components get like the most access to like everything. Like your maintenance laptop, who you want to like sort of push software updates and configs, you often see that thing sitting on like all the buses, so it kind of can just look at anything. Same thing with something like a bit processor, right? That thing's trying to harvest all of the bit results, and it wants to give you some coherent status of how this thing booted and how it's working. So that's going to have a tremendous sort of visibility across the system. And as we look for things to attack, all things being equal, we're going to look at things that have the most ability to sort of talk to other things. What else? So this is sort of how I was talking about how we want to keep sort of pushing down the stack on this stuff. We're working with the customer. We're talking about things we're finding. We're evolving our understanding of the system with them based on documentation they're going to give us, source code they're giving us, conversations with developers, etc. And in the back of my mind, I'm always trying to build this picture here, right? And this is normally an interesting exercise with the customer to try and get to common language on these things. What's your architecture? Oh, I don't know. It's a whatever. It's a navigational. I'm like, I don't care about what it does. Show me where the computers are. They're like, what do you mean? I'm like, literally, where is a microprocessor and what's running on it? What kind of computer is that? It's like, I will say it's amazing, but I think it's just, different sort of, people have different ways of doing business, right? And it's, there's always an activity to sort of normalize on language and get people talking. There's often this discussion we have with like sort of the network security person. And I understand Nick, those, they have a job, right? And we are not there to like mess with that. But if you tell me, hey, we do all this work with like VLANing stuff to make sure things can't talk to each other. Okay, and we have all these firewalls in place, stuff like that. Okay, that's cool too. And we normally get this position where I'm like, I will assert that all those things work perfectly. Like you don't have to worry about I'm not worried about your firewall configs or your VLAN management. What I'm going to say is these things need to talk to each other. There is a link between like that, maintenance laptop to the comms processor. It has to. You told me that this is the path for sending data. And usually there's he's like, oh, okay, I get it. Fair enough. But this is sort of the language that my team wants to talk about. It's like, where are the computers? How are they compiled? What are the security settings on those things? What are the key processes and how do they talk to each other? And even down to what are sort of the data formats they're passing around, right? And where are those handlers? The more information you can give me and my VR team, the faster we can get up and running and the more efficient this process is. If you tell me this is the guy who wrote the sort of tactical message handling code, and here is the functional test that he wrote or she wrote, and here is the .h file that has all of the definitions for those messages, I'm like, yes, we are talking the right language now. I can write a fuzzer for that in like an afternoon, versus if we had to do this blindly, it might take 5 months, right? So here's sort of the vulnerability research process, which we showed in the OV1. To this day, you see a lot of research papers, et cetera, about automating, and automation is good. I think from sort of Codex's perspective, most of the value in automation for us is to point smart people to the places where they can make the evaluations of whether there are bugs here. So sort of human in the loop, sort of automation assisted is kind of where we use a lot of tooling. The tool that basically looks at your binary, your source code, and it says, I found the bug and I popped it and I automatically wrote next to executable. Just don't like work or exist. There is still, a tremendous amount of sort of crazy thinking that VR engineers, hackers do. And you really need to sort of put them in the position to evaluate how things talk to each other, how you can misuse them, how you can force them to misbehave. So we do a decent amount of source code auditing still. There is, I swear to God, a guy in Melbourne, Florida, and he prints out C code and he walks around the office reading it on printer paper. And he's super, super smart. He finds tons of bugs. Like, if that's your thing, cool. We build a lot of custom binary tools. You know, again, we use disassemblers and things like Ghidra, even though we have the source. You know, I always make the joke that's like, even if you give me all the artifacts of how you built this system, I still like have to reverse engineer it. Like, in order to get to like the zen of how this thing works, I need to sort of walk through what you did. And there's still effort there. It's not nothing. And we have, you know, a long tradition, you know, in the industry doing dynamic analysis, building fuzzers, building emulation frameworks, building the ability to run 6 million fuzz tests a day on a system to find crashes and easily triage them and rerun them in context to find, you know, what caused them. So we still do that a lot, and I'm going to explain why this is still a pretty big part of our workflow. So how do we do this cooperatively? Sort of the old-timey VR process was sort of like, you know, all this reverse engineering, et cetera. But we get cool things like, give me access to your source repo. Let me see all your old bug tickets, right? If you guys found bugs in the past, I can go look at code that looks like that. We can find bugs. Give me all your build environments. You know, for a couple of reasons, right? To see if you're building securely, but also maybe I just want to roll this thing straight into AFL, recompile your code, and like run fuzzers on that. You know, the easier you make it for me, the better. So, you know, normally we're coming from pretty mature sort of developments when you're talking about sort of modern weapon systems supporting infrastructure. So they've got lots of testing. They've got lots of virtual machines they probably use already. You know, maybe even they've written custom emulation of weird architectures that we can reuse. Specialized test group. I will put a caveat on the VMs. This is just something we've learned in the past few years. We come into this, like customers, especially ones that are running, you know, part of their systems is a more traditional, let's say x64 environment. Like, oh yeah, we've got a whole virtualized test system that you can just use. And the first thought is like, sweet, give me the VM and I can just boot it. And then you find out it's like a 4 VM sort of setup, and they all have to come up together. And these VMs are configured to require like, you know, 32 gigs of RAM each. And they don't, like, we spend more time trying to get other people's virtualization solutions up and running than half the time we're just like, we could have just rolled that ourselves. So just something to think about. All right, assisted fuzz testing. I'm going to talk a little bit about this. I will just read this. Lots of modern commodity software already subject to extensive fuzz testing during development. Google, Microsoft, etc. If you're building sort of really well put together, really, you know, billion-dollar software, you've got a security team. You're fuzzing the heck out of this stuff before it goes out the door. And, you know, if you think that I'm going to walk in the door on like Google Chrome and point some like dev random fuzzer at that thing and it's going to fall over, it is not. There's a reason that those bugs, you know, you can sell them for a lot of money. But so I'll just bring this up here for all of our developers. I've been trying to push this for a while. If you're writing your own code, especially if you're writing anything in sort of non-memory safe land, you really should be fuzzing that stuff yourself. Again, anybody who writes C code or C++ code, if you've got header files, if you've got unit tests, you're already in a perfect position to sort of beat that code up and find the bugs before they ship. It'll take you like 1/10 of the time that'll take like the bad guy. But guess what? Like the bad guy is willing to spend 1,000 times as much as you are to find those bugs. So, you know, David Brumley's been pushing this for years. You guys, you know, track him. He works for All Secure. He's got lots of articles on this, sort of integrating fuzzing into modern development environments, CI/CD, you should be doing that if you write software. So what are the modern issues with like fuzz testing on modern software, right? You get these large code spaces. Difficult to explore all the code, even with intelligently generated inputs. It is not unusual for us to set up, spend time learning about your system, figuring out sort of the data sets that you use those as seeds for fuzzers, and build a moderate sized like fuzzing infrastructure that's, let's say you got, I don't know, 20 or 30 cores on it, point that at a system, 6 months, and never get any crashes. You come back and that's like been hitting the same sort of code pathway for 6 months. And then you have to go find a way to sort of undo stuck states, et cetera. There's also sort of this large upfront setup effort. Hey, I'm going to build this virtualized farm of computers, and I've got to have sort of a test harness to manage it, and I need to find a way to find and triage crashes. If these are like non-x86 computers, maybe I need to bring QEMU into this, or maybe I have to write some sort of custom emulator. I mean, that is a tremendous amount of work. And a lot of modern VR people, I think, will just tell you that they don't do it anymore. Eric, do you agree? He doesn't. I would not use this. But why would we use this for like our efforts then? We have help. Again, we can punch through a lot of those problems because we have access to the developers and their data sets. Using existing test data from functional testing, unit testing, to target specific code locations. So I don't spend as much time in sort of stuck states. If there is a key piece of software, like a parser that I want to get to, I could go to a developer and he says, yeah, I wrote a functional test for that. This thing will get you right into that. It will prepare that software state for you, and it will then get to that code. That is awesome. That's really where I want to be seeding my tests. What else? And the other piece is, we spend a decent amount of time getting systems to boot and operate in their intended modes and states, right? If you're working from sort of a black box RE world. Hey, I've got this binary running and it's booting and it's crashing. Okay, you got to go figure out there's some config file that has a specific setting in it that it needs it set in order to turn this light on in order to get the thing to boot. Or, oh, this thing expects to talk to your bit processor during boot in order to make sure that that handshake's successful, and it's going to send some token over the wire to make this thing actually work. That's all work that we basically have to go through. But again, doing this cooperatively, we go talk to the person who wrote that and say, oh, I have a test unit for this. It'll just get that system right to where you need to be. Super, super nice to sort of save that kind of time. So this is one of the arguments why we still incorporate a lot of fuzz testing in the CVA process. And here's some other ones. Well, I'll just go back real quick. So there is still a lot of C and C++ and assembly code deployed on systems out there. That's 30 years old, more. It was developed in environments which were not thinking a lot about security when they were initially designed. And because of the nature of these systems, nobody's like pounded on this stuff. We still see pretty trivial kind of stack-based buffer overflow type of stuff where people are not compiling with stack canaries or proper runtime protections, sort of trivial like parser type stuffs where config file parsing, will knock over the system. There's just a lot of code, right? If you think about, let's say, the US military industrial base, there's billions of lines of code that have been deployed on systems that are still need to be used for decades, right? And anytime you talk to these developers, these owners, they talk about the long tail, right? Which is great, you found this bug and we're gonna fix it. But we've got 3,600 systems deployed all across the world, which basically have to be updated manually using some sort of CD that needs to get shipped. It's not a great system for rapidly fixing systems or to sort of maintain sort of high security systems. So, you know, yes. Well, the good thing is, right, that even outside of the cyber world, software updates exist, right? Any systems that's under active development or even a maintenance contract, it's going to get software updates. So, a lot of times, literally, you're talking about dropping CDs into the mail and shipping them across the world to the person who's the sort of system owner at that remote location with like sending an email on the side that says, you're going to get a package. You need to update these. You can also think about how horrible that is. The fact that I could send, like a CD to say, hey, you need to install this. But there are mechanisms in place that just they weren't thinking about this, and it's tough. Now, I'm definitely not going to say that every system in the world is like that, right? Some systems are naturally sort of better equipped for some of this, right? You've got like a satellite system, right? Those things are already need to be updated, remotely. So you sort of have some ability there. But sort of other kind of physical systems, they still are maintaining these sort of logistics lines, which involve physical updates. So not super responsive. Any other questions? Yes. Sure. Like I used to work on embedded crypto systems back in the way back. So we had over the air software updates to those. So if you've got something like a software radio or something like that, sure, they have the ability to pass that stuff, encrypted over the wire. So that's a thing. But it's still, it's not the same thing as pushing an update over the internet, right? It's still an order of magnitude more complicated and annoying a process. You're definitely not going to get into something that's like the CI/CD world where you're finding bugs, you're patching them, you're testing them, you're pushing them like 8 times a day or something like that. When I worked in that world, you're talking about updates still 4 times a year, something like that. So that's sort of, yeah. How does it work? I mean, I don't think it works any differently than threat intelligence in the commercial world, right? Like, what do you know about the people who are trying to target your systems? What do you know about the specific tools and techniques and capabilities and goals of those adversaries? Perhaps the ways in which you get that information are a bit different, but I think it's still the same sort of use case modeling and sort of threat modeling that you would do on even a more open system. The threat intelligence itself, I guess you'd say that. I mean, there are people who spend a lot of time thinking about, threat modeling for, U.S. weapon systems. And, there are ways to get that information. No more questions. I'm joking. So we're gonna go through some lessons learned, things we've seen. So here's a good thing. There's a lot of secure design, that was being done 20, 30, 40 years ago, right? Think about we call it like high side systems, red, black, implemented systems. There was a lot of thought put into the requirements. There was a lot of evaluation of code back then, a lot of serious testing on things that were considered critical, and that's helpful. A lot of sort of secure gatekeeping type code, which is kind of stuff that I was writing 25 years ago. When you're talking about like, what we used to call sort of system high design, where there's stuff that's trusted and there's stuff that's not. There's stuff that's encrypted and then there's stuff that's not. And that sort of gate between that needs to be super, well tested and well designed. And you had, dozens of sets of eyes looking at that, and that's good. That's a way to make good. What's the bad? One of the bad things is, while a lot of times, sort of people in the binary exploitation world are really looking to get code execution, run their code, and you sort of pop up Notepad. If you're talking about a supercritical system in a mission environment that needs to be up all the time, every one of those fuzzer crash tests that I found is basically all the stuff that we would probably throw out if we were trying to actually get code execution. You got to fix all those bugs. Definitely don't want these systems, being taken down in the middle of some sort of engagement, or even worse, someone having sort of a deterministic sort of replay attack where they can just hit you over and over. And every time you sort of reboot, you can turn off, say, that comms computer. So, a lot of times when we're talking to customers, I'm like, do you want us to go further with this? Like, this is probably exploitable, but it's also a crash that can be deterministically thrown, so you should fix it. What else? The good. Complicated embedded systems are still hard to understand, even with all the source code. I had a note in here about, like, is this hard VR? I think a lot of VR people would probably say in some ways no, because you're still dealing with a lot of sort of, unsecured C and C++ code. But the hard part really is how sort of weird these systems end up being with, 3 different architectures, 4 different programming languages, weird, non-standard to most people sort of bus, messaging and stuff like that. So there's still an upfront lift in order to get to a state where you can understand how you can stimulate the system, how you can crash it, how you can sort of build your threat model. And that's good. That's sort of a security through obscurity type of thing. But it's not nothing. Also, it's not unusual, right, where you've got 4 different contractors on a system writing different style code with different levels of capabilities. So it's just this big heterogeneous sort of mess for, if you're a VR person. Again, it's a little higher lift. The bad, I said before, there's still a lot of legacy unmanaged C and C++ code out there. Anytime we look at any embedded system, right, I'm just like, where's the C code? I have a statement which I will make, which is any non-trivial C code, C program that's more than 1,000 lines, that's never been sort of banged on, is exploitable. It's just the complexity problem alone is hard to manage. Trying to understand and how this thing's going to work in every corner case, that's where the bugs are. Yes.
How difficult would FPGA architecture testing with it? That's what my background.
Yeah. So here's how we normally attack that, and we get this question a lot, right? What's the FPGA going to do? If you're telling me that FPGA is implementing like a system on a chip, running like an embedded processor, I can look at that like a normal processor, right? Like, well, I wouldn't have it on an FPGA if it wasn't like that, because there's all these other pieces on here, filters and computation things in there. We turn that sort of into a simulation problem, right? Where it's like, okay, what I want to do is I want to emulate, let's say, the microprocessor portion of the SoC, but then I need to sort of build this sort of gray box of that where the data comes in and where it goes out. And again, that is super, super hard. If you have developers involved, if you have all the design documents, it gets easier, right? Do you have a MATLAB model that you use to test this in the first place? Cool, give it to me, and I will use that as an input into the thing that's trying to get this target into the right state so that you. That makes sense?
Yeah.
Yeah. But people come to us all the time, right? It's like, well, what about all the bugs in the FPGA code? I'm just like, that's a super hard problem. Yeah. Just leave it there. Bad. Lots of custom build environments, lots of custom configs. Also say a lot of older build environments. It really drives me crazy when you find people that are compiling code without stack protections on, without ASLR turned on, without NX, and you ask them why, and they'll say one of 2 things. We never thought about turning that on. This file's been like around for 20 years, and it just never occurs. Or we're afraid it'll break the build. And you're like, have you tried? And you're like, nope. let's just see if it'll build this way. It's almost impossible in modern development environments to compile that stuff out. But there's just a lot of, the embedded world, there's a lot of old tools out there where people don't even know. They're like, version 7 of this, they implemented like NX. Oh, I didn't know that. So all you developers out there, I don't know that this applies to anybody in the room. Understand, the tools you're working with, the architecture's running on, and sort of the security protections they can already provide. So that's how we find sort of exploitable bugs that wouldn't exist in sort of a lot of modern systems, because they're just sort of still in this sort of legacy mindset. Here's another thing, and this is more sort of generalized VR thing. You compile your code and you ensure that it's it's got all the security features turned on and everything. And then you link it to like 7 libraries, and you don't bother looking to see if those libraries have like been compilable with security protections turned on. You kind of have to think about the whole picture here. Same thing with like, if you're, a weapons system developer or owner, right? You've got subcontractors and you need to push that kind of stuff down to them. It's, hey, we just learned about this thing called like secure coding. We want you all to sign up to this new model. Here's another bad thing. We see a lot of sort of custom messaging, even rolled over like TCP, right? Where, I've got like 4 bits of start bit, and I've got like this field that's, a timestamp and a sequence number and a message length, and then the body data, just hand rolled like C data structure type stuff that's getting passed across the network. That stuff's filthy. I always say, so custom message sets equal custom parsers equal bugs. Parsers are where the bugs live a lot of the times. That's where so much like corner case handling happens. It's where a lot of like memory allocation occurs, trying to like handle this, you're basically asking the software to have a perfect understanding of system state, even though it has this like tiny view of system state. And when we talk to customers, the first thing I asked is like, okay, where are all the parsers in the system? I don't necessarily care about your core processing functionality. I believe that you know how to write, like, I don't know, some sort of DSP style functionality that you chose to implement in C, but then you had some junior engineer implement like the config parsing piece that goes there. That's where the bugs are. Custom text for, same thing with config files. This is places where we still find sort of issues. My recommendation here is like, there's existing data formats out there. There's existing tools for writing sort of configs that sort of been beat up over time already. Use them. This is one we still see, which is crazy, is sort of message that get passed over the network to just tell a system to do something, like reboot or change modes or whatever. You have some sort of, let's say, mission computer up there that's trying to manage all these assets below it, and which makes sense. But if I end up on that same network, you've just given me a handle to like just reach out, like poke the system and like shut it off. We even see places where you'll see like messages like passed as strings over the network, which then get passed directly into like command. And executed, so like sort of trivial sort of command escaping and injection over the wire. I haven't seen as much of this lately, but it still happens, and that's sort of like that's outside of the C++, memory world, right? Like you see Java code that does this. People that are using these sort of like direct passing of like sys. I'm just gonna go quick here. I think I'm a little over time. Embedded systems build up state. Like if you've got, I don't know, you've got like a radar system, and then you've got that connects into some sort of battle picture management system or whatever. These things, they're building up state as you go. So it's not like some sort of transaction where it's like you send a message and it either handles it, it doesn't, it goes back to state 0. it's continually building up all this message state, which it becomes very unpredictable and very difficult to manage. This is the last thing I'll talk about. These are just two concepts that I've sort of thought about. I think this illusion of distance is probably familiar to anybody who's sort of like in the penetration testing world. People who think because there's lots of systems between the attacker and the target means that they're like far away from each other, when in fact it's like, no, if you meant for there to be a comms path between those 6 computers to your computer, they're like right next to each other. It doesn't matter that all this other stuff's in between. You've given me a channel to talk directly. This other one is sort of illusion of trust type of stuff. If you think about like a message coming out of like, over the air, an over the air sort of encrypted message. Like, wow, that's really hard, right? Nobody's going to attack that. What are you going to do? Crack the crypto, build your own SDR, and send messages over here? Good luck. Like, okay, well, that thing connects to like a much larger network that has 6,000 contractors on there who each of them developed with different methods. Each of those systems play different roles in the system. Like how trusted is that thing now? That sort of blob. This is no longer a cryptographically secure communication channel. You basically just like, it's just like a TCP. You're trusting every single person on that network that can touch you to be a good actor. And that's just, to me, that's not cool. You shouldn't do that. That's about all I got. Any questions? Thank you guys so much. Enjoy the rest of the conference. Thanks, man. Appreciate you. Oh, hey, how's it going, Brandon? Yeah.